Now we'll look at some examples where we can actually use the bound we derived on the error for using the alternating series test. Let's consider one series, and again I want to go through several different ways we might use our knowledge of error bounds with that series. So the alternating series we'll consider is the sum from 1 to infinity of -1 to the k over k squared. Importantly, this is alternating, and we could use AST to show that it converges. So the first thing I want to do here is find an upper bound on the magnitude of the error in approximating this sum by its fifth partial sum. So reading this, we want to see that what we're really asked to bound is the absolute value of what we've called e sub 5. From our derivation of the error bound, we know that this should be bounded above by the absolute value of the 5 plus 1 or sixth term of this series. Importantly, this tells us to disregard the -1 to the k because I want this to be a positive number no matter what, and simply to plug in k equals 6, and we get that this has an upper bound then of 1 over 36. Now, given that the fifth partial sum here is actually equal to -47 over 60, use your answer to part 1 to find a lower and an upper bound on the sum of the series. So this is going to require a little extra thought because right now we have seemingly only an upper bound. But in particular, we have to notice that that's just an upper bound on the size of the error. So in order to answer this part of the question, I need to start thinking about my relationship of S5 to the actual sum of the series. And this comes back down to looking at whether this series starts with a positive or a negative term. So what we know so far from what we've done in part 1 here is we know that 1 over 36 is an upper bound on the absolute value of the fifth partial, or excuse me, the e sub 5. And that e sub 5 is equivalent to the sum of the series minus the fifth partial sum. So part of what we want to do is establish how the sum of the entire series relates to what we found in part A. And so we see that it comes in here. Because for this series, the first term is negative. Again, we know that because it starts at k equals 1, and it has this -1 to the k in there. Then thinking about our pattern, so if the first term is negative, if I think about S1, then adding the first two terms would give me a partial sum of S2 that's upward, and then S3, and then S4. So what I'm establishing by doing this little sketch off to the side is how the indexed partial sums relate to the sum of the series, which would be representative of that dotted line. So because the first term is negative, what I know is that the sum, which I'm identifying as S here, is going to be greater, and in this case I mean less negative by saying greater, than any odd indexed partial sum. And odd index includes S5. So what that means is that when we're talking about the infinite sum minus the fifth partial sum, I know that that's positive. And I'll point out if the first term were instead a positive number, we would be able to do a similar sketch here and see that this difference would be negative. So we always have to do this on a case-by-case basis. Now, what does this mean then about talking about the absolute value? Then our bound from part 1 implies that, so let me look back at part 1. So in part 1, we ended up with this statement, which I translated to what we have here. So we're saying that the size of the error is bounded above by 1 over 36. Because I know that the error is now positive, I can instead translate that to the statement that the infinite sum of the series minus S5, which again, this is exactly what we mean when we say E sub 5. Knowing that this is actually positive, then saying that the absolute value of this difference is bounded above by 1 over 36 is the same thing as just saying that this difference is bounded by 1 over 36. If I knew that this was negative, then I could say that this difference was bounded below by negative 1 over 36. So that's the distinction I'm making here. But because it's positive, then I know that that bound on the absolute value truly serves as an upper bound on this difference. And because it's positive, then I know that a lower bound is 0. So at this point, I can add S5 to all three parts of this inequality. Giving me this. And so knowing the value of S5, if I wanted to come up now with bounds on the sum of the entire series, the last thing I'm going to do is actually substitute in for S5 negative 47 over 60. And this would be like this. So this is the way that I can take information about a bound on the size of the error and translate it to a statement about a bound on the sum of the series. And like I said, for alternating series, we just have to take a little bit of extra care because when we're finding an upper bound, it's always going to be an upper bound on the size of the error. And so I have to go back and look at the series to determine if that error would truly be positive or negative. And then one last thing to consider with this, like we've seen with the integral test, I could change the unknown here. So if my question were instead phrased as the following: how large should n be so that the size of the error, and using the nth partial sum to approximate the infinite sum, is bounded above by 1 over 100. So we come back and think about what we know the error is bounded above by. We know that the absolute value of E sub n is bounded above by the absolute value of the next term, which I'll write as the absolute value of A sub n plus 1. So it suffices to ensure that the absolute value of A sub n plus 1 is bounded above by 1 over 100. Again, to think about why that's true, if I know that E sub n is bounded above by the absolute value of the next term, and I know that the absolute value of the next term is bounded by 1 over 100, the key thing is that 1 over 100 would automatically imply an upper bound then for the size of the error. So now this gives us something to solve. We want to make sure that A sub n plus 1 in absolute value is smaller than 1 over 100. For this series, a sub n plus 1 looks like 1 over n plus 1 squared. I don't include the negative 1 to the k part there because we're taking the absolute value. We want that to be less than or equal to 1 over 100, which says that I want 100 to be less than or equal to n plus 1 quantity squared. I want 10 to be less than or equal to n plus 1. And then subtracting 1 from both sides, we want 9 to be less than or equal to n.